Hello everyone. Today I'm going to look at this paper which reads Reference Resolution as Language Modeling. This paper has come out at Apple quite recently, actually, 29th March, so around 1 week back. I was curious to understand what Apple is currently doing in the space of large language models because we have seen LLMs being released by OpenAI and Google. Where is Apple in this journey? This was where I wanted to understand, and uh, that's why I want to read some of the papers that they have been uh, releasing recently. So we are going to go through this paper. I do not know what reference resolution is currently, but hopefully I'll try to understand this in detail as we go along. Okay, so let's start with the abstract of this particular paper. So it says that reference resolution is an important problem to understand and successfully handle contexts of different kinds. The context includes previous turns and contains two non-conversational entities, such as on the user screen or those running in the background. So they have written that while LLMs have been extremely powerful for variety of tasks, their utilization for reference resolution remains underutilized, and this paper demonstrates how LLMs can be used to create an extremely effective system to resolve references of various types. So let me try to see if I can document some of the things that we have learned over here. Okay, so we are going to read about reference resolution, Apple. Okay, so within the abstract, what we can see is that LLMs have been used to make reference resolution very effective. This is all I have learned so far from the abstract. And let's see what exactly is reference resolution as we move along. So they say that human speech typically contains ambiguous references such as they or that, whose meaning is obvious to other humans given the context. Being able to understand the context, including references like these, is essential for a conversation assistant. Okay. For instance, consider the following interactions. So, they have given a bunch of examples of what exactly is the meaning of reference resolution. So, uh, let's say the user tells the agent or the AI that show me the pharmacies near me, and then the agent gives the user a list of pharmacies, and then the user asks questions like example 1, call the one on Rainbow Road, or call the bottom one, or call this number which is present on screen. Now here we are not explicitly mentioning call this pharmacy or call this pharmacy, etc. We are referencing something which is related to that particular pharmacy. So this is something which is quite obvious for a human, but it's probably not so obvious for an AI or an agent. So here it's not immediately apparent for the agent to understand or complete the user's query without the ability to comprehend context. So comprehending context seems to be one of the let's try to summarize. This seems to be one of the important tasks. Comprehending context is important for LLMs. It is not natural, uh, useful for voice assistants to enable more natural conversations with humans. Okay, so this is good. Let's try to look at some of the previous works that have happened in this area. So they have said that recent LLMs have enabled end-to-end experiences. Uh, now, what they say about these end-to-end experiences is that firstly, when a framework runs completely on a device, on a system such as a smartphone that has a limited computing power due to the low power nature of the system, using a single large end-to-end model is completely unfeasible. Using using a single LLM for this task would usually require the use of a very large model with long prompts and true end-to-end experiences. I'm guessing this is what ChatGPT also does. It's an end-to-end model uh, in which a very large model is embedded within the system. Second, consider the case when the model has to integrate with APIs and has to consume information from components upstream. This often requires a large language model and a complete overhaul of existing pipelines, which might be cumbersome or completely unfeasible. Third, the use of a focused model would allow for an existing reference resolution model to be swapped with improved versions in a transparent way. Okay, so essentially, what they are saying is that uh, using end to end models not feasible on smartphones because typically people are going to use smartphones when they are interacting with their voice assistants due to low computing power, need to have much smaller and focused models relevant for reference resolution. Okay, so let's try to see exactly what this means also later as we move along. So in this work, they have advocated the use of a relatively smaller language models but fine tuned for specifically and explicitly the task of reference resolution. So that's the advantage or the novelty that this paper is bringing. So this is kind of the novelty also which this paper brings about. There have been some papers along similar lines relying on language modeling alone. So it's not a large language model anymore, it's an LM, which is a language model. It does exceedingly well on tasks that can be modeled in a sequence to sequence fashion. However, the biggest challenge with adopting this technique of a voice assistant lies in resolving references to entities on the screen. We'll come to what exactly this means, references to entities on screen. Essentially, we are trying to get the LM to see. In other words, we are trying to have the language model to have eyes. So this is something which this paper talks about, and what it talks about is on-screen uh, elements resolution using language models or LMs. I have went through some of the paper ahead also, and essentially enabling LMs to see. I just want to give you an example of what exactly do they mean by this. And this is a screenshot I have taken from the paper itself. So imagine this is the on-screen entity, uh, which is there on the screen of the user. Now, uh, I'll be asking a question which is not a direct question, but it references to something. So, for example, uh, what is the number given at the bottom of the above image? So ChatGPT 4 answers it correctly. I can even say what are the directions to Queen Anne. I hope you are understanding the meaning of reference resolution in the context of an on-screen entity. This is an on-screen entity, and we are giving queries to this on-screen entity which have some references within it. For example, number given at the bottom, what are the directions to Queen Anne, etc. Uh, okay, I have to explicitly mention image here in the above image. Says the image doesn't provide directions, but if you are looking to get directions to the address listed for Queen Anne, which it definitely identifies correctly. Okay, so we'll have a look at more examples as we move along, but primarily try to view reference resolution as something which we also saw in the introduction, where the users say that call this number or call the one on this street. uh, Instead of uh, directly asking the question or the query in a direct manner, you reference it to something. And what they have done in this paper is that they have developed a language model which is specifically trained to understand on-screen queries. Of course, now we are seeing that GPT-4 is also doing a good job. Let's try to see what is the value this particular paper is bringing to the table. In this work, they propose reconstructing the screen using parsed entities and their location to generate a purely textual representation of a screen that is visually representative of the screen content. To the best of our knowledge, is first to work to use a large language model that aims to encode context from a screen. So this is a novelty they are bringing, reconstructing the screen using parsed entities. The paper talks about reconstructing the screen using parsed entities. Okay, so in the next section, they have given what is the related work which has happened in this particular field. So we are going to go through some of the work that they have mentioned. While traditional reference resolution systems have explored conversational and visual references in depth, resolving on screen references is a domain that has been relatively unexplored. On screen references differ from the other because they tend to be more structured and highly textual. User queries around on screen elements often tend to be more action oriented rather than Q&A based. Uh, Vision transformers have recently gained prominence in a popular step in tasks that require visual understanding. However, these need to be trained on natural real world images rather than screenshots of on screen layouts, which has a very different distribution. In addition, they can be very expensive to train. I have made a note of vision transformers. I am not sure what these are, but I'm going to read about them in one of the future sessions that we have. Recently, visual transformers have become popular. Mostly, they take in complex images and require more computational power. Okay, so there are generally, okay, so before we move to the next paragraph, here they have given another example of a reference resolution. Call the business number which is given on this page, and the objective is to extract the number associated with the business landline from the raw image. and these models need to parse text to be able to perform this particular function, a process which can be complex and computationally intensive. Bearing in mind that the underlying text and its location on the screen has been referred by a system, and as a consequence can be relatively easily extracted without a large complex model. Okay, so there are two particular papers which they cite, Attis et al. And Bhargava et al. These papers are pretty closely related to the work that they are doing. They have mentioned two drawbacks of these two works. I would encourage you to go over these drawbacks. The purpose of this session is to understand mainly what is being done in this particular paper, but I would encourage you to again read these remaining sentences over here. I am also going to make a note of two papers that uh, should be read to understand the literature in detail, and Bhargava. So, if this topic interests you, then I would 100% encourage you to go over both of these papers, because they have also used a language model to capture on screen entities and parse the on screen text to be able to decode the entities. But they suffer from some disadvantages which are mentioned nicely in this particular paragraph. So they have given the task at their hand in a very clear manner. Basically, what they want to do is that the relevant entities that they want to capture, which are pertinent to the user query, are on-screen entities. These are entities that are currently displayed on the user screen. Conversational entities, for example, call mom. The contact for mom would be the relevant entity in question. Then background entities. These are relevant entities that come from background processes that might not necessarily be a direct part of what the user sees on the screen. For example, an alarm that starts ringing or a music that starts playing in the background. For example, if your music is playing in the background and I'm interacting with an AI voice assistant, I might ask the AI agent to stop the music or to stop the alarm. So they have divided the different entities that we are going to encounter into three types. On screen is something which the user is seeing on the screen, which was similar to the screenshot which we just saw in chat GPT, like this. Conversational entities is something which there is a textual query which is linked with something else. For example, pick the alarm which I have set in the morning. To understand this query, the AI needs to first understand, okay, morning means what time exactly out of the entire list, and then they have to pick the corresponding alarm. So it's a two-step process. You don't directly say pick the alarm at 8 a.m., because as humans we tend to naturally assume that the person that we are interacting with is understanding the reference in which we are asking the particular query. So we pose the task of reference resolution as a multiple choice task for the LLM, where the intended output is a single option from the entities which are shown on on the user screen. So let's actually look at what this exactly means. Uh, since I've gone through the paper, I think it's a better idea to expose you to this particular thing pretty much directly. Okay, so let's say the user's request is save the address, and we are looking at this particular image, let's say, or we are looking at an image which has three different addresses which are mentioned in the image. So the entities which will be shown to the user, or which is the ground truth, will have all the different addresses, which include the postal address, the email address, and the URL. This becomes the ground truth. Then switch off the one reminding me to pick up DD. Then here is the one which is the ground truth, which is option number 3. So here you can see there are multiple number of ground truths. Here there is a single one. The first one, call the one on Rainbow Street. Again, this is Rainbow Street, so this is a single ground truth. Now this is the testing where they are trying to understand the model output. Call the evening number. So obviously the model output should be 4 over here. Remind me to get printouts before the tax deadline. So then the model needs to understand, okay, tax deadline is mentioned over here, and the printout reminder should be sent before Feb 15. So the model output is number 2. Here I think it should be number 1. Take me to the one in Washington. So it's over here, number 2. Save the link to the breakfast recipe. So it has model output 1. So these are qualitative examples of LLM based fine tuned model able to adapt to complex use cases. I have shown this to you to help you understand uh, these paragraphs. So the task of reference resolution has been posed as a multiple choice task in which there is a ground truth and there is a truth which the model is predicting. So task of reference resolution is posed as a multiple choice task. Okay, so now let's look at the kind of data sets that we are going to have in this particular paper. Our data sets comprise data that was either synthetically created or created with the help of annotators. Annotators would mean graders who have actually sat down and created the data by themselves. Each data point contains the user query and a list of entities along with the ground truth entity. For example, in the previous examples that we saw, there were a list of entities and then there was a ground truth based on that. So they have taken three different data sets here: conversational, synthetic, and on screen. So let's try to understand what's the meaning of all of them. Conversational data would be data that is collected for entities that are relevant to user interaction with the agent. So for this, this has been done by annotators, graders who are shown screenshots and asked to provide queries that unambiguously references an arbitrarily picked entity in the synthetic list. For example, if the grader is shown a list of businesses, then they might come up with queries like take me to the one that's second from the bottom, or call the one that is located on this particular street, call the one on Main Street, for example, or call the business which deals with, let's say, this particular clothing or this particular area. So these are some of the queries that the graders can come up with, and then that becomes your training data set. Or you can divide it into a testing data set as well later. Synthetic data is something where it is obtained from synthetic data from templates. Note that the synthetic nature of this data set does not preclude from containing data points which multiple entities can be resolved to a given reference. For example, for the query plate, it can be resolved to all entities of both the types music and video. So they have not actually given an example of what's the meaning of synthetic data, so it's a bit confusing for me right now. On screen data is something which we have seen. On screen data is the screenshots of uh, uh, of what the user is seeing on the particular screen. For example, the example we saw in ChatGPT, this would be a typical example of on-screen data. They have given the process by which they have uh, condensed the on-screen example into a training data. It's basically a two-step annotation process. The first phase was for extracting queries based on the screens, and the second one for was for identifying the entities and mentions for the given query. So this is something which you can take a look at the details for the on-screen data as well. Overall, we can see that there are data sets. There are three different types. There is conversational, synthetic, and on-screen data. Okay, now which are the models? So this is the model that they have come up with, which they are calling as ReALM. The Mars is the model which was proposed previously, which is non-LLM based, and the one which is based on ChatGPT, where we are comparing both GPT 3.5 and GPT 4. So as a benchmark, totally four models are considered: Real, which is the current work; Mars, which has already been uh, proposed in this paper by Ates et al., and GPT 3.5 and GPT 4. So they have talked a little bit about Mars, which is again a non-LLM based approach. Mars extends it to conversational and background entities as well. Then ChatGPT, we are aware of this. We aim to get both variants to predict a list of entities from a set that is available. In the case of GPT 3.5, which only accepts text, our input consists of prompt alone. However, in case of GPT 4, which also has the ability to contextualize on images, we provide the system with a screenshot for the task of on-screen reference, which we find helps substantially improve performance. So typically, when we are using the voice assistant, we won't be providing screenshots as such, but it should be able to look at the screen and understand what's happening. So that's, I think, still one step ahead, um, where we are interacting with an AI voice assistant, which also has the ability to look at exactly what's going on in our screen, unless we upload a direct screenshot. So as we have already seen, I also tried using a bunch of examples. Chat GPT-4 is really good in understanding contexts. So I got a very good accuracy when I used multiple examples. I even tried to use an example of a Domino's menu card. So you can have a look at this image also. See this image, uh, and then identify pizza which has, let's say, mozzarella cheese and lowest price. So this is the menu which I uploaded, and I asked to identify the pizza which has mozzarella cheese and lowest price. Is margarita starting at 35 for medium size? So let's look at this. Yes, it does have mozzarella cheese and it's 35, I guess. So yeah, I think all of these are having the same price. So they could have given me multiple options. For example, this Hawaii, and this also has mozzarella cheese, and the price looks similar. But in a way, it understands the context as well. So let's look at the results that they have got. The model that they are comparing, the different models that we have is ReAlm. Then we have Mars, GPT 3.5, and GPT 4. These are the models that they are going to be looking at. Okay, so overall, the results that these people have got is, let's try to look at the results in quite some detail. Uh, let's look at the first column. GPT has a 97% accuracy over here, and Realm also has a similar level of accuracy. In the synthetic data, however, GPT has a pretty low accuracy compared to Realm, which has almost 99.8. On screen and unseen data, here GPT almost performs in a similar way compared to Realm, which is sometimes better, actually. For example, this is 99.3, this is 93. Let's try to look at how they have summarized. Uh, so what they say is that GPT-4 is almost similar to Realm, and they are much better than Mars for new use cases. As a case study, we explore zero-shot performance of this model on an unseen domain, alarms. The last row in table 3 compares the performance of all approaches and baselines on this unseen test, we find that LLM based approaches outperform the FT model for this test case. Among the two, we find that performance of ReALM and GPT-4 are very similar for this unseen domain. Uh, However, for domain specific purposes, the model that is proposed over here performs better than GPT-4. We find that due to the fine tuning on user requests, ReALM is able to understand more domain specific questions. For instance, consider table 4. We are asking it, can you make it brighter? Which might be related to the brightness of a device. GPT-4 incorrectly assumes the references to be only about a setting, whereas the ground truth consists of a home automation device in the background as well. And GPT-4 lacks the domain knowledge to be able to recognize that the device would also be relevant for this particular reference. ReAlm, in contrast, does not suffer from this due to being trained on domain specific data. So, overall, what I have got from this is that ReAlm is much better than GPT-4 for domain specific data, and ReAlm is almost similar to GPT-4 for unseen data. Both models perform better than the model Mars, which is quite interesting. So let's look at how they are summarizing this work, which is actually very important. In this work, we demonstrate how large language models can be used to perform reference resolution. They have done this by encoding entity candidates as natural text. Critically, we demonstrate how entities that are present on the screen can be passed into an LLM using a novel textual representation that effectively summarizes the user screen while retaining relative spatial positions of these entities. I would also request you to go over the algorithm more in detail to understand uh, this specific sentence. We show that ReAlm outperforms previous approaches and performs roughly as well as the state of the art GPT-4, despite consisting of far fewer parameters. This is what I think is the main takeaway from this paper, is that uh, the output is quite comparable with the state of the art, and it's much faster and smaller. And also, it outperforms GPT-4 for domain specific user utterances. So, this is something which I want to just write it down. uh, ReAlm, similar to the performance wise GPT-4, but much fewer parameters, so less computationally intensive, as the LLM has been specifically trained for the domain specific data. So, this brings us to the end of this paper. I hope this gave you a background of what this paper is trying to do. What is the meaning of reference resolution? And in the context of the current LLMs, where does this particular paper by Apple stand? Uh, it is through a series of papers that I think Apple is going to finally release its LLM to the world, but it helps to understand the new papers as they come along. You can see the improvements are marginal from paper to paper now, because the biggest advancements have already been done. But still, these marginal improvements are very useful, because imagine later there is a small device which you're carrying in your pockets, which is your own personal assistant. You want that device to know exactly what is going on in your screen, right? To be able to give you uh, a much more personalized response. The current voice assistants that we have, they are not very human like. They seem very artificial, and they also make a lot of mistakes. So the objective of this paper in a way is to bring these assistants as closer to human like assistants as possible, and to make the conversations more natural, in which humans often use a lot of references. I believe GPT-4 has already tackled understanding references and contexts in a good way, but since it's an end-to-end model, there is a lot of parameters on which the model is trained, which makes it very computationally expensive. So more smaller models with small set of parameters like ReALM can be definitely explored for this purpose.